Okay, we're almost there. Two more things here, which will help us. This last one's really important. It gives us our construction we need for hyperbolic geometry. So the theorem said that a circle, other than the circle of inversion, is going to be fixed by the inversion. All the points aren't fixed, but the circle gets mapped to itself, if and only if it's orthogonal, intersects the original circle at 90 degrees. The corollary to that says if we actually have these points, if P and P prime are distinct points that are images of each other under an inversion, circle with center O, radius R, then any circle containing both of those points is going to be orthogonal to O. Okay, the corollary follows directly from the theorem, but here's just a picture of what's going on. So we have the circle with center O, radius R, and we have this point P. We're trying to find a circle that's orthogonal here. We have the point P and the point P prime, okay, which is the image under the inversion. Okay. We could find that center. If you have 2 points, we could find the perpendicular bisector, and that would pass through the center. That would be one way to find the center of that circle. Okay. And then we could draw the circle, and once we do, we could find these intersection points. I could use those now to actually draw the tangent lines. And I've added the angles in. Oops. So these, it works at the other one as well. So it turns out if I have P and I have its inversion, and we do the circle that goes through those 2 points, which would have to lie on the perpendicular bisector there. And actually, that's not a single fixed circle. As long as that point's on the perpendicular bisector, this second circle will be orthogonal to the original, which means that the 2 lines going to that point of tangency, the intersection point there, if we draw these 2 lines, the radius of the circle, and extend them, we get right angles. So all of this together, and I know it's a lot, but the big result is we actually have a way to create orthogonal circles given 2 points inside the circle, and we're going to need this for hyperbolic geometry when we look at it later for the model. So the problem is, given a circle with a center O and radius R and 2 ordinary points P and Q that are not collinear with O, try to construct a circle. For hyperbolic geometry, the model is going to be inside the unit circle, and P and Q are both going to be inside the circle. But we want to be able to take P and Q and create a circle that goes through those points that's orthogonal to our original circle. Okay? We can do that by finding the image of either or both of those. Yeah. If we have P and Q, we can find P prime and Q prime. Find either one of P prime or Q prime and go through PQ in that point, and it'll be the circle we need. Just let me show you that.